So my name is Pantelis Antoniou, and I'm working for Konsulko group, and I'm going to talk about something called device tree portable connector. So how many of you have worked with community boards like one of those, like Raspberry Pis? How many of you have developed expansion boards for those development boards? How easy was it? And for something even more difficult, how many of you have ported your expansion board to a different development board so that it works? Was it easy? So I'm going to talk about this problem, and that's one way to actually solve it. So a few years ago, things were much simpler, so because there weren't any development boards available, or they were really expensive and they were like a few K each. But now we have many inexpensive development boards. The definition of open source hardware differs, but we can say that all of them are open source friendly. So we have Raspberry Pis, the BeagleBones, Linaro's 96 boards, which is quite recent. We have the C.H.I.P, which there is another session about it in a few hours, I think. Orange Pis, Minnowboards, and a ton of others. So if you have an application, and you can definitely find an open source hardware board to help you develop it. And you do that, or just think it up with embedded Linux, or you can use it for learning how it works. But mostly you use them to do something cool with it. So you can do 3D printers, you can fly drones with it, water your lawn, or whatever you want, whatever your imagination can make you. But what are expansion boards? Are simply plugged into a physical connector. There's some, every development board has a manual that describes the connector and how you go about connecting things to it. It might be a single pin row or more. You get power, electrical signals, and most of the times it just directly connects to the SoC pads. So you have to have some knowledge of how that SoC configures those pins to be what you need them to be for your expansion board. And turns out that the modern SoCs are quite complicated. And for someone that's not an actual professional working on board support or on a silicon vendor, it's pretty complicated. So how do you make your expansion board work? You just connect wires. So in a mental level, it's simple. So you have pins that are your UART, you have I2C, you have GPIO lines, and that's the mental model is simple. You just configure your expansion board to accept signals that are one set of device or another, and then it should work. But you have to find a way to describe those connections and the peripheral configuration for Linux to work. And while there are many ways to do that, we're going to talk about how to do that using device tree. In theory, you can do that with ACPI, or you can do it with a platform C files, but this is how you do it. So in a very general manner, this is a device tree configuration. It's not very complicated. It's just a set of nodes and a few properties that say that this is what kind of device it is, some properties that describe what it does, and you're off and it works. But it's exactly the same as if the expansion board was soldered on the board. So there's absolutely no difference there. That means that you have to be intimately aware of every kind of configuration option you need to get your peripheral to work, even if it's on the expansion board connector. And you need to get everything absolutely right. If you make a mistake, if your pin maxing is not correct, or something that needs detailed knowledge of the SoC port, you're gonna have problems. So if any of you have worked with the BeagleBone, you know all about those steps. So the BeagleBone is a very common open source development board, and it has a pretty complicated pin maxing configuration. So you have to read the schematic of the expansion board. You have to write down the pinout, the configuration of each and every pin. Then you have to go to the reference manual of the BeagleBone, figure out which mode you have to put that pad pin in order to work. You have to then go to the hardware reference manual of the specific SoC, figure out which pin max register applies, and then you have to switch manuals, go to the technical reference manual of the SoC, and find out what pin max value you have to configure to the device tree entry for the pin max. So this is, if you have to do that, a lot of times it gets really complicated, and it's easy to make a mistake. Things don't work, and it's really time-consuming. So the configuration is SoC specific. You have to figure out the configuration. That's hard. If you get it wrong, many times you don't have any indication of what's going wrong. You have to just look at everything and try to figure out what's going on. But as you see, there are many community boards that have compatible expansion connectors. So you have Arduino compatible boards, you have R.Pi compatible boards. Grove is a very common expansion connector scheme. You have 96 boards, but they don't work. You have to have a specific configuration for each board. It's like, imagine that you had a PCI card and you had to write configuration for each different board that you connected to. So but there has to be a way to get it easier. So what would it take to get it to work? So we have to make expansion boards work in every board that has a compatible connector. We have to simplify the expansion board definition and remove any kind of SoC-specific configuration. And you have to make these things to work easily. Because actually, baseboards are commodities now. What's really important is the expansion board and the application that you run with it. So why not shouldn't I be able to switch boards easily and take all my work, plug it to a compatible board and make it work? And that's what PCI does, and that's what's sane actually. So you can make all the baseboard makers to compete in a level playing field. So you don't have to have a huge development community just for your own specific baseboard. You can switch boards easily, and that means you avoid all this fragmentation that you have, because we have, each different development board has a different community, the sizes are different, and while people are doing the same thing, they're not actually part of the same community, because it doesn't work. You have to work specifically on that board community. And another thing now that we have on ARM, if we have multi-arch kernels, and if we have portable connectors, you can generate a kernel and a root file system that would work exactly the same on every board. So that means the community is a single one now. So we get to the point of what a device tree connector does. So it's an XCon driver class. It's not an exact match, but it seems to work. We might need to modify a few properties of the XCon driver class. We did that by defining some new constructs. We have a way to define the connector, a way for mapping what functions the connector provides and how they're mapped to the SoC and the board port. And we have two new constructs called bridge drivers and proxy drivers. The bridge driver is something that is an intermediate driver for mapping the connector resource to an internal resource. And a proxy driver is a construct that directly translates what the driver does on the connector to the SoC. So we'll see what's the difference later. So if you open the manual and you see what a connector, how a connector is defined, actually it's defined by its physical connector. So you have a connector, typically a connector number, and then a connector pin number. And you can easily express that using the device tree reg property. So it's a pretty easy map. So we have its connector node describing a pin, and you have certain properties that are unique for its connector pin that are defined for the connector driver. So you have a way to describe the connector, you have a way to describe the function of its pin. So you have to have a way to do that and say, okay, I can support these kind of functions on these pins, and then I have this limitation of how these pins can be used together. And you have properties that a driver is either a bridge driver or a proxy driver can use to map the resources from the connector to the SoC internal. So a bridge driver is a bridge. That means, let's say you have a connector that offers GPIO pins. So the bridge GPIO driver would present a single GPIO driver for all the pins on the connector that can be configured as a GPIO. So even if you have a really complicated GPIO scheme, so some pins come out, some GPIO pins come from directly from the SoC, or some other pins come from a onboard GPIO expander, you can use that as a single GPIO driver, which makes things more abstract. So you don't deal with the internals of the board at all. You just deal with what the connector defines. So the proxy driver, it uses configuration from the function part of the device tree, and you can request pins set to a specific configuration, and you configure them for everything to work automatically. There's a device target, which is the device template of what's going to be used when you instantiate that driver. So let's say you have a connector that defines a UART, and you have a UART configuration possible on certain connector pins. You use a UART proxy driver that says, okay, I want a UART on these set of pins, and then everything is set up so that the proper board UART driver is instantiated without any specifics being declared for the portable connector. So let's take, I know this thing is a little bit complicated, but we'll have some proper examples, and I really need questions and I can answer them so that we can see how everything works. So a real example, there are a lot of BeagleBone capes, which are expansion boards. It's a pretty popular board. There is a mainline kernel, cape support is available. There is extensive pin maxing options for each pin on the connector, which means that the connector infrastructure is stressed because there are some combinations that are really weird, like some pins are shared for every expansion board, like the I2C bus where the identification EEPROM is there, and some pins are actually connected together, so you cannot configure them independently. So it's a good selection of peripherals that cover a lot of the corner cases, so we can figure out if things work or not. So how does it look? In essence, it looks like this. So you have a device tree, connector driver, you declare it, and you have 3 nodes called connector, functions, and plug. So the connector device tree bindings, you have the standard way of addressing the pins. You declare number of address cells. The BeagleBone has 2 connectors named P8 and P9. So the first address cell is 8, which means connector P8, and the pin number is 3. You have all the possible pin max configurations that you can apply, and you have a name of the SoC pad that this connector is connected to. You need to configure pin maxing for each pin of the connector for it to work in the desired configuration. That's the way you describe it. You have AM3XX pin max node. This is defined on the base SoC. Everything is defined now in the base SoC DTS. So this is not part of the connector description that you're going to write for the driver. And you have the configuration exactly as it is when you're having a normal driver. Pin maxing is pretty complicated, and it's the thing that most of the people that work get wrong, because it's really esoteric. It shouldn't be, if you think about it, a developer that works with an expansion board doesn't care about the internal SoC specific stuff. He just needs his board to work, and he knows how to configure those pins. But he doesn't need to know the internals of what pin max register I should set and to what value for my thing to work. And I don't want to do that same thing for, I don't know, 5 or 6 compatible boards. I just need a definition that works everywhere. So the connector driver will handle all the pin max setting. You have a list of enabled pins that you can look up for which pin max configuration fragment to apply when a driver uses them. But as it is right now, the pin control driver doesn't support that, because when you set a state for pin maxing for its driver, it's all or nothing. So you cannot do piecemeal addition of pin max fragments to a running to the current pin control state. So you need a patch for that, and you completely remove the need for any to set any pin maxing. It's just automatically done. Now you have a function. What is a function? A function is, let's say, a UART function or an I2C function or a GPIO function. It's something that you configure a few pins of the connector to do when you enable a driver that uses them. So you have a function node for its different function, and you have the bridge drivers are completely free-form. You can do whatever you need with them, because there is code that actually reads that and does the configuration. But the proxy drivers, they follow a general format. So there's a typo there. Oops. So let's take a look at the GPIO bridge driver. So first thing we need is GPIO base, because if you've used, if you ever seen a GPIO chip driver, you'll see that it uses a fixed number as a base for each of the GPIOs it handles, and you have to have a starting base for its GPIO chip. That's one configuration. Then you have how many modes you support. So we have two in this GPIO chip driver. It's in and out, and then you define all the pins in the connector that can be configured for a GPIO and where they're really connected on the backend GPIO chip driver. So that's a property that's a set of 4 cells. The first cell is a pointer to the GPIO chip. The second cell is a pointer to the connector that this pin is connected to. And then the mode pin max P handles follow. So it looks a little bit complicated, but it's much simpler than if you have your pins and your connector labeled properly. It's exactly the same thing as it's in the schematic. So you just type the correct values there, and you're good to go. So why the GPIO driver is a bridge driver? Because it actually provides services to other drivers on the connector. So we have an example there where you have a relay expansion board, and those relays are configured as LED drivers. I know it's and that LED driver references the connector GPIO driver, and you need a way to. There's no way to describe that as it is with a simple mapping function. So you need an intermediate driver to forward the request to the real GPIO. So let's take a look at a few things about the proxy driver. So you have a UART function driver. You list what kind of parameters are required. So you have an RX and TXD pin, and you can have optional properties like RTS, CTS. Those are usually, some of them can be connected to a UART function, or some of them can actually be GPIOs. So you need a way to describe what happens when you have a GPIO property that works there. So that declares the format of the driver, but then you need an actual way to describe what kind of UART devices are there on your SoC, how you get them, and what are the maxing options. So you have, let's say this is a UART number 2, and it points to the UART number 5, which is on the board. Which is the GPIO controller for that UART, and then you have a list of nodes that are the maxing options. So those are a tuple, 2 cells for each option, and that means that you can have the transmit pin of the UART can be connected to the UART5 TXD connector pin, and it uses the UART5 TXD pin max option. And for the RXT parameter, you have 2 options. You can either connect it to the UART5 RXT or UART5 CTSN pin on the connector, and those are the maxing options. I2C is simpler. Now, there's not a different proxy driver for its different function. All of the proxy functions are the same, and they just use different properties in the function nodes to be configured. So, and finally we have plugged, which is just a simple bus on the connector definition, which can be easily be a target for overlays. Any device that's dropped there will be instantiated. And if you remember about when the discussion about the overlays was taking place, there is a security problem with overlays that you can point an overlay everywhere, and you can really mess things up. It's not foolproof regarding security. So using the connector, you only have a single target where you can drop overlays, and the connector driver will make sure to have all the devices be instantiated in a way that you don't break out of the cell of the connector. The security is much better. So let's say we have, that's an example of a real expansion board called BeagleBone UART, which simply configures 2 pins on the connector to be a UART without flow control or any other external pin. So that's all you need. You have the compatible string, which is dcon UART, which is a proxy driver. You enable it, and you just say, I need this to work on these pins. And if the connector can satisfy the request, it will just work. So you instantiate the proxy driver, the connector will find the UART function node and will parse the parameters that were defined and figure out which connector pin is connected, which pin max option I should apply. We'll find which UART of all the UARTs that are supported in the SoC best matches your requested configuration. And when it finds a device match, it will just enable the pin max option for those pin functions to be enabled. All the properties of that node will be copied to the device that is pointed at. It will use a change set to enable that device in the backend, and that's it. You have a UART that's exactly the same as having it on the baseboard, but you haven't used anything board specific to make it work. So this is an example for an expansion board with a relay having 4 ports. How you describe it, you say that's a simple bus because you have more than one device that you want to instantiate. The first device is a GPIO controller, just using those pins that you want to use, which is P915, P923, P912, P927. That GPIO, DT-con GPIO will work as a GPIO controller. And that's the other device, which is a GPIO LED device. That's a standard Linux device. It's not a connector device. And you just point to that GPIO chip driver, and that's it. And you'll get it to work. So you will create, the connector will create a DT-con GPIO device using the pin list in the device tree configuration. That means you have a GPIO chip with 4 GPIOs with ordering that were defined in the pin list property. The driver, the ttcon GPIO driver will figure out which pins are available from the backend. It will request them. And will create a GPIO chip driver that is connected to the backend GPIO chips. And when the LED driver is probed, it will request the GPIO pin, and it will be forwarded to the real GPIO. I had that working, but there was a major GPIO layer rewrite, so I have to remake the patches before everything works. I will submit them next week when I'm back from here. Yeah. When those patches are going to be upstream. That's the question. When those will be available? But even if I post them, it will take quite a while to get all the kinks out, get the bindings correct. So for most of the standard devices that you have on an expansion board, that works. We have a broken GPIO patch because there was a GPIO rewrite. And there is a problem with cascaded GPIO operations. It works, but the pin request flags are not set correctly. There might be some problems there with the GPIO maintainer. We need an extra patch for making the pin maxing work and add pin max options to a state dynamically. And we will need bridge drivers for all hardware classes that provide services to other drivers like GPIO, PWM, and I cannot think of anything else right now, but you will need that, and we will have some time working with mainline to get there. So that's it, and I really need to take your questions for as long time as we have, because this is a complicated subject. And yes? Wait.
So right now, those bridge drivers are basically drivers which implement like a GPIO chip, like all the callbacks, and then you call the callbacks and they forward it to the real one. Have you thought about maybe instead of having this kind of like forwarding driver, just forward the lookup and then directly send the calls to the real one?
That's what it does. It doesn't implement everything that it needs a backend driver, and it will forward the request using the GPIO chip methods.
Yeah, it will forward the call. So you have like a set direction callback.
Yeah, all the callbacks that you implement.
No, but what I mean, instead of forwarding the callbacks, just forward the lookup. So that it then returns.
There's no API for that in the kernel right now.
Yeah, but you can add it.
Yeah, that's...
That's my question. Have you thought about it?
Yep, but that will take input from the GPIO maintainers, and it might be really invasive. So the idea is to have something that works, and if we can figure out a way to fix things, we can do that in the future.
Okay, thanks.
But the thing is that it's completely abstracted, so even if there's a change in the backend, your connector definition should work. Anyone else? Yes?
So besides yourself, do you have much buy-in from the GPIO maintainers on this concept?
No, because I have broken GPIO right now. So when I start posting patches, I expect a major flame war, but I'm used to it. Anyone else? Gentleman back there?
can you model cross-pin constraints? Pin 5 can be GPIO or RXD.
Yep.
Another pin can be GPIO or RXD, but not, it can't be RXD if pin 2
Together.
is, right?
Yeah.
That kind of thing.
It should be possible because there's a pin list and everything is being kept track of.
So you can detect the error, but
Yep.
can you,
Fix it? No.
well, can you find if there's multiple ways to map that, can you solve the problem or?
It should be possible because it's a common problem. It's not uncommon to have multiple mapping configurations. And if you've seen what was set in the definition of the UART driver, some UART drivers have option for hardware flow control. Some UART drivers only use GPIOs. So you should be able to map transparently. So let's say the connector driver requests flow control pin, but it's not available as a real hardware configuration. You should be able to generate a GPIO configuration for that pin. Anyone else? We have plenty of time, and I'm a lousy singer.
So it looks like setting this everything from the device tree looks quite complicated, at least for me. Did you think about some easier way of setting this from the user space, for example, from config.fs or something like this?
Well, from config.fs, you just load an overlay, you apply it to the plugged node, and then it will do that.
Yeah, but the description is quite complicated. Maybe it would be easier to add some more easier interface.
What kind of an interface you would need?
I mean, create connector, create function, do the mapping.
Okay. So, but you still need the driver for it to be created, right?
Yep.
Okay.
But it can be loaded and
Okay. I'll think about it.
just the usability, nothing more.
Yeah, you should be able to do something that will generate a connector description from user space. But you can do that completely in user space. You don't need the kernel to do it because it's just a device tree blob. Yep. You can have a script that has a set of UART configuration set. So when you do that in user space, you can just say, okay, I want a UART to be present on pins, I don't know,
Yeah, but
6
you
and
have
5.
to generate the blob and write the blob, etc. So
Someone has to do.
binary
someone has to
blobs
do it.
are already hard to read.
You don't have to read it. It's going to be a script.
Yep. So, as you like, there are different options.
Well, we cannot put everything in the kernel.
True.
Anyone else? Yes?
It sounds like after you specify both the bridge driver and the proxy driver, and when you run the two connector for the board, you still have a ambiguity for certain pin connects. Not necessarily it will connect exactly what you do. So in that case, what do? You still further modify your drivers? I mean.
No drivers are modified. All the drivers that are the backend drivers, the SoC and the board drivers, are completely unchanged. You only modify the device tree properties of the device node that will be created when you request that pin configuration.
So this is by the functions, such as I have like multiple ground pins or multiple power supply pins, or the power supply has different values. In that case, that your drivers cannot differentiate those pins. They connect very particular or very accurately.
So you need extra properties for its pin configuration?
Yeah, because in your parameter, you just specify this is a power pin, this is a ground pin, and I have multiple, and I have different values, and how do you further specify that?
Right now, it doesn't work for power pins. But if it's when those patches are out, you're welcome to command, and we'll figure something out. It's just like you need an extra configuration for each pin, like what kind of I don't know voltage level you support, or pin configuration, or where the board is powered from, right?
So another thing is that, like you said, the pin will connect or relate to the register address. Can you?
Yeah, that's a standard way to describe addressing in device tree. So it's just a connector. For my examples were just a connector number and a pin number, and you can have multiple. So let's say you have ground on 6 pins. You can define 6 reg addresses that where your ground pin is. So it's not a single address on its node. You can have more. Well, let me show you. So is that something? Is that similar to what you're saying?
Yes. Yes, correct.
Okay, so it's not a single address for its connector. You can have multiple address ranges. Oh, wait, it's up here.
Right. Yeah,
Yeah.
that's exactly what that looks like. Okay.
Okay.
So in terms of the node is on the device tree, the software node, or
It's a node in the connector driver. It's named connector. Let me show you. Maybe it's easier that way. It's just very large, and I cannot put it in the. So you have the DT connector driver, and you have a connector node. You define what the reg addresses are going to be, and then you have, for each pin on the connector, you have a definition. It's a big connector, and you have plenty. And for most of the pins, it's a single reg property, which is the connector number and the pin number. But then you have stuff like ground or voltages, and then you have multiple options like this.
So in the case, like if I have like you mentioned the transceiver and receiver, if I have like multiple transceivers, like 4 or 5, how the transceiver link can be mapped, or how do I specify it in the parameter driver?
Okay, the transceiver is a function, right? That means on the connector you have a transceiver function that might use different pins.
Yeah, but I have multiple links. How do I specify that? And I do not want
So
to
when the driver is instantiated, it should be the connector driver should perform a mapping and figure out what combinations are available, and then plug in the backend device driver the transceiver options that would make your device to work.
Sounds still like lots of manual work.
Yeah, it's a complicated subject. If you have a specific use case that you can describe, you can always comment on the patches, and we'll figure it out. Everything is brand new right now, so it's going to take some while. Anyone else?
So just on that example, you got modes up there for GPIO 2.6. Why are some of the mode blank? Does that mean the modes are?
They're not available on that.
But what's the order of those modes, and why is the order significant that you need blank?
This is just for debugging, for textual debugging. So you have a register that has 3 bits for mode configuration, and those are.
So this is
the value. So this is for the GPIO 2_7 connector pin. You have LCD data 1, and then you have GPMC A1. That means that the max register is going to be set. That field is going to be set to 0 or 1, and then the next one is not available. The next one is number 3. So it's debugging aid.
So the actual order is not
It's the order of the...
significant to the driver. The driver
No, it's not
looks at the
significant to
name.
the driver, it's only for debugging.
Okay.
So that when you look at the max register, you can say, okay, without having to look at the reference manual, what the mode configuration is. Anyone else?
What is a trigger or usage trigger to the detection of the portable device tree?
Excuse me?
What is when the upgrading GPIO is happened?
When the GPIO configuration is applied. So you have
driver initialization timing.
It's all part of the driver. That example with the LEDs and the relays. So when the LED driver is probed, it will request a number of GPIOs, and then that GPIO driver will request a GPIO pin. And since you know which direction, if it's input or output, the GPIO bridge driver will figure out which pin maxing option to apply, and then it will forward the request to the real GPIO chip driver.
So the driver probing timing, then GPIO values are updated. Right?
Yeah.
Oh,
So if there's no GPIO request for the pin is left as it is. So someone has to request the pin for it to, for the configuration to be applied.
Thank you.
Okay, anyone else?
Are your slides online?
Yep.
Are they, I didn't see them in the conference page yet.
I upload them today.
Okay.
Like a certain group of a pin involved in certain version of the firmware, is there anywhere to specify that?
Yeah. Let me show you. So you can look for max options here. So this is definition for UART5, and you have a set of different max options for the RxD pin, and so that means the connector driver will try to find out which max option to select, so that in order for an RxD pin to be configured. Yeah, it's a little bit hard to follow if you don't know exactly how device tree works, but that's a pretty low-end, low-level definition. In reality, you shouldn't be able to deal with it at all. You just have some kind of overlay driver coming up, figuring out what board is connected and applying that overlay, and you won't see that at all. Or you have a canned configuration for your hardware and say, okay, load the configuration for this port, and it would just work. Yeah.
So where's this overlaid device tree stored? Is that on an EEPROM on the CAPE board?
That's up to you completely. So for my case, it was easier just to put it in the root file system in lib firmware, and you have a driver that reads the EEPROM and then applies the configuration. Now, you might not want to do that. You might have a very limited selection of boards. Let's say you have 2 or 3. You can use a GPIO pin to be configured as ID, and then you select between the few variants that you support. But it's up to you. Hardware is really diverse now, and you cannot find and figure out beforehand every kind of way that the problem will work. So some people store it in NAND, in a special sector. Others just put it on the kernel command line, or some others do it on runtime when the kernel boots. You have a specific case?
No, I was just thinking of best practices. It seems like putting on the hardware itself might be the most flexible because you don't.
Right. So since the connector driver is really abstracted, I do not expect that bindings will change much. But doing the same thing with a standard device tree overlay, which is a real SoC specific binding, those bindings may change. But this might be more future-proof. I don't know. If we get the binding right, I think it's much. You might even be able to put it in an EEPROM in the board itself. Anyone else? Yeah. Okay. Thank you.